Have you ever wondered what happens when you try to quickly turn off a motor, a relay, or a solenoid in an electronic circuit? These are all examples of what we call inductive loads, and they can behave quite dramatically when you try to switch them with a transistor. Inductive loads present significant challenges for transistor switches, primarily due to their ability to store energy in a magnetic field and their inherent resistance to sudden changes in current. When a transistor attempts to rapidly interrupt current flowing through an inductor, it generates a large, potentially damaging voltage spike across the transistor, and it slows down the switching off process. The core reason for these challenges lies in the fundamental behavior of inductors, which oppose any change in current. This opposition is quantified by the relationship voltage equals inductance times the rate of change of current, or V equals LdI over dt. When a transistor switch opens, it tries to force the current to drop to zero very quickly, causing a very large negative rate of change of current, or di over dt. This rapid change generates a substantial back electromotive force, a high voltage that can easily exceed the transistor's breakdown voltage, leading to its destruction. Furthermore, the energy stored within the inductor's magnetic field must dissipate. If not provided with an alternate path, this energy will try to force its way through the now open transistor switch, resulting in overheating or immediate failure. This also contributes to a phenomenon known as slow turn-off, where the inductor's current cannot drop instantaneously, holding the transistor in its partially conducting region for longer than desired. This increases power dissipation and heat generation in the transistor during the switching transition. To mitigate these issues, engineers often employ protective measures. The most common solution is the inclusion of a flyback diode, sometimes called a freewheeling diode, placed in parallel with the inductive load. This diode provides an alternative path for the inductive current to circulate and safely dissipate its stored energy when the transistor turns off, preventing voltage spikes. For more critical or higher power applications, snubber circuits, which are combinations of resistors and capacitors, can be used to absorb and dissipate the inductive energy more effectively, controlling the voltage and current waveforms during switching. Understanding these effects, often referred to as inductive kickback or flyback voltage, is crucial for designing robust and reliable transistor switching circuits. Properly managing the stored energy and voltage transients not only protects the transistor from damage but also ensures the longevity and efficient operation of the entire system. Ignoring these principles can lead to unreliable performance, excessive heat, and premature component failure.